Now, what you just saw was inspired by that meme. I call it the trunk lid LED panel, and I thought that would be a fun project to create simply because one of the few things that bothers me when I'm driving is when people drive behind me and blind me with their headlights. And so I figured this would be a suitable, petty solution to that problem. Now, does it make sense to simply change lanes and then let the person drive past me so that I'm not being blinded anymore? Does it make sense to simply reorient my rear view mirrors and have my pursuer's own lights reflected back at them? Or does it make sense to even just simply keep driving along and ignore the problem? Of course not. A much more convoluted solution was necessary, and that's where this comes into play. The trunk lid LED panel's final design can be narrowed down to 3 simple electronics. The LEDs themselves. Their purpose in the design should be fairly obvious. They simply shine a bright light at the would-be pursuers after the trunk lid has reached its fully open position. A door lock actuator was used in order to release the trunk lid so that it's actually in its open position, and then linear actuators were used in order to raise and lower the trunk as need be. To power those electronics, 12-volt batteries were used, and to control those electronics, I needed to create a circuit that had a microcontroller. And that's what actually makes this entire design possible. That's what allows me to cycle through those different events that I talked about. Going into this, I had little understanding for how circuitry or electricity actually worked. So I took it upon myself to start about as simple as I possibly could, starting with a simple 5th grade science project. I grabbed a couple wires, a 9-volt battery, and a light bulb, and I combined these components together in order to figure out how to light up the light bulb. Once I understood how that worked, then I moved to adding a switch to that same circuit, and this allowed me to understand how I would eventually implement a button into the final design. This is also what allowed me to begin working on my first prototype. Before I began modeling my first prototype circuit, I needed to decide on a microcontroller to use in order to control the 3 electronics that would be in the trunk lid LED panel. So I went with the Arduino Uno because of its simplicity and because of my familiarity with the Tinkercad software. Tinkercad allows me to model a circuit, code that circuit, and then simulate that circuit so that I could ensure that it's working properly before physically building it. When I modeled my first prototype circuit, my primary challenge was making so that one button would control 3 electronics. In order to make that happen, I needed to delve into some simple programming. So I programmed it so that the button would, on the first press, it would activate the trunk release mechanism, and then after a delay, it would turn on the LEDs. The second button press would then deactivate the trunk release mechanism, it would turn off the LEDs, and then it would activate the trunk closing mechanism. There would be another delay, and then finally the trunk closing mechanism would turn off. And then, because of the way I set up the code in a switch case break scenario basis, it allowed me to be able to cycle through these steps multiple times, so that again, if I wanted to, I could use this multiple times in the same drive. After this was all done, then I needed to be able to implement this to the actual electronics, and that's where the next main device came into play, which is the relay. In the simplest way I can describe it, a relay is simply an electrical switch that can only be turned on or off depending on whether there's current running through it. Since I can't directly control 12-volt electronics using the Arduino, I instead use the Arduino to control relay channels, which would then indirectly control the electronics I needed to control. So when I designed the second iteration of my circuit, I simply included relay channels. The code itself remained relatively the same. I only had to make a few slight adjustments to it in order to account for the relays. The final circuit design included a total of 7 relay channels. The first and second iterations included 3 only, because only one relay was needed to represent each distinct electronic. But for the final design, in order to control everything, I needed to have all 7 relays accounted for. 1 for the door lock actuator, 1 relay for each LED panel that I designed, and then 2 relays per linear actuator in order to control them completely. Now, along the way, in between the second and third design process, I ran into an interesting problem where having the button placed on the center of the breadboard here would cause the circuit to behave in unpredictable ways, where simply touching a wire or shaking the table would be enough to cause the button to register a press. But by simply moving the button to one side of the breadboard, so either here or here, would change that completely, and then the circuit would behave normally. And so I moved the button to its own separate little mini breadboard as a final design iteration, just to keep the button out of the way from all the wires. And as you can see, I did include a 3D fixture to keep the circuit a little bit cleaner. So I 3D printed this fixture, modeled it. Unfortunately, I deleted the design, but this is what the fixture looks like. And then I simply screwed in the electronics to keep them from moving around too much. In order to get the trunk lid to raise, my first idea was to use a simple mechanical device known as a trunk spring. The way that a trunk spring works is that when it's installed into the trunk lid, while the trunk lid is in the closed position, the spring is in tension. But the moment that the trunk is released, the spring will compress, forcing the trunk lid to fly open. I abandoned the use of this design for two reasons. The first is because when the linear actuators, which were part of my final design, were installed, they would not allow the spring to compress and make the lid fly open. And since the actuators were already controlling the extension and retraction of the lid, it seemed pointless to have the springs in there. The second reason was because I realized that my final designs for my light panels were too heavy for the springs to be able to make the lid open, unless I put them to a dangerously short length in order to make them generate more force once they compressed. Implementation of the door lock actuator came with 3 separate challenges: how to fasten it to the trunk lid, where to put it in the trunk lid, and how to get it to actually pull on the trunk release cable. Now for the first problem, I decided to use zip ties to fasten it. However, the problem was that the zip ties, they did do a decent job of holding it in place, but it wasn't perfect. Unfortunately, whenever the actuator would pull on the trunk release cable, it would move inward, rather than simply staying in place while the cable was pulled. The second problem was that the zip ties needed to be so tight around the actuator that they ended up crushing the gearbox, rendering it inoperable after several uses. So I dispensed with the zip ties and I moved on to door number 2, which was to use 2 screws to fasten it in place, which was what it was designed for. But this is what leads into problem number 2, which was where to put it in the trunk. Now unfortunately, the trunk does not have a flat, uniform shape. Instead, it's curved, it has concave features throughout, and so I needed to figure out how do I get this to be in a not awkward position so that it can pull on the trunk release cable and be as close to parallel as possible with it. Luckily, the center of the trunk had a fairly flat surface that was also close to the exposed trunk release cable. So that was where I decided to drill my holes and then place the actuator. For the third challenge, I needed the actuator and the trunk release cable to be as close to parallel as possible with each other. The reasoning for this is because when the actuator retracts, I need it so that the trunk release cable will retract in the same plane, because if it's retracting in a different plane, then the release cable may not be pulled as effectively in the direction I need it to go in order for the trunk lid to open. So to solve this problem, I used the securing mechanisms that were provided with the door lock actuator in order to create a custom part that would allow me to connect the two in parallel. Now, the part itself does a very good job of doing just that, and the trunk lid does open very effectively when using this part. However, it's not perfect because it can slip off over time, or the screws can loosen over time, which would lead to an ineffective trunk opening mechanism. So this isn't a perfect design for that reason, because it needs to be continually maintained in that way. Being that this was my first exposure to linear actuators, one of the challenges I had was figuring out the correct size to use for the trunk. Measuring the trunk, I had a difficult time because I wasn't exactly sure which hole to use in order to put the linear actuators in. So I started with a 14-inch linear actuator. I found that this was the incorrect size and eventually moved down to 12 inches. To ensure that the trunk lid would open and close properly, the linear actuator needed to be bolted down at both ends. I did determine which trunk lid hole to use, but I still needed to figure out where on the trunk floor or the trunk wall to install the other end of the actuator. I found a thin metal wall between the cabin of the vehicle and the trunk itself, and that served as my anchor point. So, I drilled one hole into both the driver's side and the passenger side of the vehicle, and then I installed one actuator to each end. Now for the fastener problem. This was probably by far the most annoying aspect of this entire project. To fasten the linear actuators to the trunk lid, I used a simple long screw and a nut. However, the issue with this design was that while trying to figure out the exact distance I needed to extend or retract the actuator to get the trunk lid to open all the way, let's just say I bent quite a few screws in the process because I wasn't sure how far to extend or retract it. So this created a situation that was a nightmare to get the screw not only out of the trunk lid itself, but also a major pain to get it out of the actuator. Now I decided to go with the cheaper actuators over the expensive ones. The expensive ones overall are much better because they have superior speed, force output, and position control. But the problem was that they were almost 10 times the price of the cheaper ones. In order of importance, the characteristics I was most concerned with the linear actuators would have been positional control first, then speed, then force output. The more expensive ones had the most superior positional control because they had adjustable inner limit switches. They also were faster, which would have been nice for the trunk lid opening and closing, but it wasn't a super big make it or break it thing. And again, force output was only for when we're dealing with highway speeds. We'll get into that in more detail here in a moment. Now, because I didn't have the adjustable inner limit switches, I had to get creative with the code. If I had the option to use inner limit switches, all I would need to do was simply turn the relay connected to the actuator on or off. And then once the inner limit switch was reached, the actuator would be forced to shut off. And that's it, I wouldn't need to do anything else. But since I couldn't do that, I instead decided to write a program that would have the actuator operate on a time. Figuring out the exact amount of time I needed for the actuators did require a little bit of trial and error, meaning I had to sit outside with my laptop and then mess around with the times until I got exactly the amount of time I needed for the actuators to extend and retract to the desired length. Once the code was fully written and I had ensured that every mechanical component and electrical component was functioning as intended, it was time to put it to the test with a full functioning prototype. After the success of that test, then it was simply a matter of building it in the car. Now the only major issues I had with building it in the car was the major mess of wires that came from the relays to all of the electrical components. I eventually figured out to solve this problem by simply banding all the wires together as best as I could, as neat as I could. I did a pretty amateur job, but it still does the trick. And then, of course, writing down on a piece of paper what everything went to in the relay. That way I could keep everything nice and organized and it wouldn't take quite as long to try and figure out what goes to what. The only final issue I had with the final design, which could probably be easily solved with a bit of soldering, was that the components that were connecting to the relays themselves, the small wires, were slipping out of the relays. This is the relay that controls the linear actuators. As you can see, there's exposed wire coming out of each of the relay ports. Now, unfortunately, if another wire or piece of metal were to contact these, it could cause a spark or a short circuit. And I can't simply jam the wire in any further. It can only go so far because it's a bit longer, as you can see right here. So, to alleviate this problem, I got these smaller square-shaped wires, which will allow me to put them in all the way into the relay, and there won't be any more wire exposure. Also, I need these smaller wires because, as you can see, the ports here are rather small, and the larger wires that I have don't pair very well with these small wires. Everywhere where there's a wire coming out of the relay, a second wire needs to go in place, as that other wire connects to either the battery or the linear actuator. Alright, you guys, one last thing I'm going to touch on is the aerodynamics associated with this project. We can't neglect the drag forces acting on the trunk lid of the vehicle while it's in motion because we want to know whether it's going to stay up or not. So to do so, we need to look into the drag coefficient. Basically, that equation at the bottom there is what's going to tell us what the drag forces on the trunk actually are. So if my car is traveling on the highway at any arbitrary speed, this is the direction the drag forces are going to hit the vehicle at, which includes the trunk lid. Since it's a big wall traveling at like 80 miles an hour, basically we're probably going to have a high drag coefficient. At least that's what I thought. But I also have two actuators that together are outputting a total of 500 pounds of force. In other words, as long as the drag force does not exceed 500 pounds, the trunk lid should stay up in theory. So I found this helpful table online, and after doing a bunch of math, there's the total math if you want to see, these are my results. Basically, we're good. From 0 to 200 miles an hour, the trunk lid's going to stay open just fine. And there you have it. That is the trunk lid LED panel. That is my first delve into an actual engineering project. Going into it, I had almost no knowledge of how electricity or electrical engineering worked. So I'd say that's where the majority of my learning came from. But I got a pretty decent amount of just understanding mechanical components a bit better, and also more on the actual design process. Now, this project, I will say there's quite a bit of flaws that I don't like, that if I had the time and the money to, I would definitely improve on. So maybe at a later time I may consider going back to it. I definitely don't like the actuators I used. I would have much preferred using the much more expensive, higher quality actuators. And I definitely would have liked having a better LED panel overall, because I didn't like using just the small LED bars with simple kitchen cutting boards. I would have much preferred an actual LED panel, more true to the real original design. Overall though, I'd say this definitely does a pretty decent job of turning this meme into a real life. So I hope you guys liked it.